All right, so we're doing an integral with trig substitution. There it is, the integral. Here's the process to follow. All right, so a couple things to say at the outset. We need to assume that the student knows something about finding derivatives of trig functions and some trig identities. Okay, so these either need to be memorized or maybe they'll be given in a formula book. Okay, so we're going to have to assume that knowledge. And next is when I hear trig substitution, I think of triangles. And so we need to draw a triangle. So here is the integral, and we're going to draw a triangle. And let's just think about where these things come from. Because so how do we think of this? The numerator should look like a piece of Pythagoras, right? So it's the hypotenuse squared minus one of the sides squared. Okay, so that's one side. Then the other side is the square root of that, and this hypotenuse is the square root of that. So if you square this, you add it to the square of this, you get the square of this. Okay, so once you get this triangle, it's with this angle theta. Now we can start to try to make this thing out of these ratios. Okay, now, by the way, there's different ways to set this up, right? If I put the this square root on this side and the 2 over here, then we would be using cosine. There's different ways to set it up. They look different, but they're not really different. Okay, so this is one way. All right, so we have sine theta is opposite over hypotenuse. Okay, so we have the numerator, right? We made the numerator. We don't want the 3, so I'm going to move that over to the left. I have an x here, so I've got the denominator partially, but not all the way, right? I need an x squared. So then you need to think of the cosine. Okay, the cosine is 2 over 3x. That's got an x in the denominator. I want an x squared in the denominator, so I'm going to square the cosine. Okay. So I'm just trying to make this thing. Okay, we got 4 over 9, which we don't want, so we'll move that over to the left. And now I've got x squared, and now hopefully you can see that if I multiply 3 sine theta times this 9 cosine squared theta over 4, I'm going to make this fraction. And we need to make dx. So we need an expression with just x in it. So let's look at the secant. That's the reciprocal of the cosine. Okay, again, we don't want the 2. We don't want the 3 over 2 expression for x. Now we want dx, so we'll differentiate each side. Okay, I just switched the left and the right there, but basically we have 2/3 times the derivative of the secant, which is secant theta, tangent theta. Okay, so you need to know how to make the derivative of the secant. All right, this is all the stuff that we need now to substitute. Then at the end, we're going to have to substitute back the tangent for the x's. So we need an expression for theta. Did I say tangent? Theta, okay. In terms of x. You could write this a number of different ways, right? You could use any trig function you want. I just chose sine. I think you'll see other answers with different trig functions here. Just recognize that they're the same. So we have an expression for theta. It's the inverse sine. Okay, and we're going to be using the sine double angle formula, and so I'm just writing what it is here. It's 2 times sine theta cosine theta. So this is sine theta there, 2 times sine theta times cosine theta there. So that's sine double angle. Okay, I'm just going to simplify it a bit. And then one more identity that we're going to use, okay, for sine squared theta. This comes from the cosine double angle. So you might want to pause here and just verify that you can see where that comes from. We're going to substitute this because this right side is easier to integrate. Okay, we're ready to go now. We got all our pieces. Okay, so here is the integral. So first substitution there. Okay. So we have to make the fraction, that's the first square bracket. We have 3 sine theta, so that's this piece, right? Times 9 cosine squared theta over 4, that's this, 1 over x squared. So that makes the fraction. Then we have dx, this square bracket. Okay. So to simplify this, I'm going to write everything in terms of sines and cosines. Well, first, no, I moved the constant outside. Yeah, okay. So, is that correct? Yeah. Should be 9 over 2. Okay. Now we substitute secant and tangent in terms of sines and cosines. So secant is 1 over the cosine and tangent is sine over cosine. Okay. Now you notice that we have a cosine squared here and cosine squared here. They cancel. Sine times sine is sine squared. Okay, looking better, isn't it? Now we're going to substitute with this. Okay, that's sine squared theta. So we have cosine. That's from the cosine double angle. Okay, now this is a relatively easy integral now because we have basically 2 pieces, a half. That's just a constant. And then we have cosine 2 theta. Okay, so the constant then is going to be 9 over 4 times theta. And then the integral of the cosine is the sine. And we have an extra 2 in the denominator. So we have 2 times 2 is 4, and then an extra 2. So that's there. Okay. And we're done with that, and we need to go back to x. So this is going back to x. Here's theta in terms of the inverse sine. Again, you could use a different function here. Let's see. So sine 2 theta, that's here. So it's a 4 over 9. And then we have, no, that's a mistake. There's supposed to be a 4 here. Okay, because you're going to have a 9 and a 4 and a 4 and a 9. Oh, that's all got to cancel. Sorry about that. That's a 4. Okay, I think my final answer is going to be correct. Just pause it to verify. We have a 4 over 9, right, from the sine 2 theta. And then we have a 9 over 4 here. So the 4 over 9, 9 over 4. Cancel. You're left with a 2 in the denominator. Okay. And that is it. Okay, final answer. All right, so yeah, you need to draw a triangle, I think. These can be, you can see these as kind of a fun puzzle, I think. All right, I hope that was helpful.